In this video, we're going to derive the equation for centripetal acceleration. And so the way it works is basically we have an object moving in a circle, right? So we're going to say that our object is right here, right? So the position of this object, we could say, right, we could represent it as a position vector, which points from the center of the circle to the object, right? So this would be our position vector. Now, if we wanted to break this position vector up into components, we could. We could say that this right here is the x component and this is the y component, right? And to define these components, we're going to say that the radius of our circle is r, right, capital R, and we have theta here, which represents the angular position of our object, right? So basically we could represent the position vector as pretty much the idea is we have our x and y components. So our x component in this case would be r cosine theta, and our y component is r sine theta, which means we can now represent our vector in terms of its components, right? Starting with its x component is just r cosine theta I, and for its y component it's just r sine theta j. So this would be the position vector of our object. Basically what we're going to do is, right, this object's moving in the circle. We have the position of the position vector of the object moving in the circle. Basically, all we're going to do is we're going to take the derivative of position to get velocity, and then the derivative of velocity to get acceleration. And that's it. But it's not exactly as straightforward as that, because centripetal acceleration is really, it's the acceleration that pretty much points towards the center of the circle. Right? It's what causes the direction of our object to change, and not the speed of the object as it moves along the circle. Right? So what we have to do is we have to take the derivative of position to get velocity. So really, to get velocity, it's the derivative with respect to time of each of our components. Okay, so to do this, right, we know that this is just going to be, right? So starting with our x component, we know that r is a constant, so we can pull it out of our derivative. So r, and then the derivative of cosine theta is just negative sine theta. And we know that we're taking the derivative of it with respect to t, meaning we have to multiply by the derivative of theta with respect to t, right? This is just a case of the chain rule. Right? And by the way, d theta over dt is just the derivative of angular position with respect to time. And we know that the derivative of angular position with respect to time is just the angular speed. So we're just going to replace that with the angular speed. We're going to replace d theta over dt with omega. Okay, so that's really just omega. Right? That's basically how that works. Right, moving on to the y component. Of course, when we're taking the derivative, we can pull out our constant r. And then we're multiplying by the derivative of sine theta, which is just cosine theta. And of course, we got to multiply by the derivative of theta with respect to t, which is just omega, right? And this is, of course, j. So this is what we get for velocity. And we're just going to rewrite this. Actually, no, we're good. All right, this is pretty much what we have now. Right? Now that we have velocity, basically the idea is, if we were to actually do the dot product of the position vector and the velocity vector, you're going to get 0, which means the velocity vector is perpendicular to the position vector, right? And that's the whole idea of how that works. Now, this would not be the case if the radius wasn't constant. When we took the derivative of the position vector, we assumed that the radius was constant, right? And because of that, that's what causes the radius. That's what causes the position vector and the velocity vector to be perpendicular to each other. It's the fact that the radius is constant, and so the dot product of position vector and velocity vector is 0. And so that's a really cool idea. So now that we have this idea, pretty much we're keeping radius constant because obviously the object's moving in a circle as well. So now that we have the velocity vector, now we got to find the acceleration vector, and this will lead us to finding centripetal acceleration. Right? Not exactly, but it's leading us there, right? So to really define the acceleration vector, we yet again have to take the derivative with respect to time of both of our components. All right, so now that we have this, right, notice how for each of these components we're using the product rule, right? Of course, we know negative r is a constant, r is a constant, but we're using the product rule because really we're doing the derivative of sine theta times omega and the derivative of cosine theta times omega. So the reason why is because, of course, like as the object moves in the circle, obviously theta is going to vary, right? So sine theta and cosine theta are going to vary. But omega will also vary, right? Because the angular speed of the ball, well, the object will still move in a circle, right? The radius could still be constant, and the angular speed of the ball could change, right? It could speed up as it moves in the circle, or it could slow down a lot, right? And so angular speed has the potential to not be constant. So really we're using the product rule, right? So when we do this, right, for the x component, we can pull out our negative r. So we can pull out negative r, and then we're doing the product rule. Remember, product rule is derivative, no derivative, plus no derivative, derivative. So derivative of sine theta is just cosine theta. And we know that we have to multiply by the derivative of theta with respect to time, which is just omega, right? Times omega, which means we have omega squared, right? And then we add that to no derivative, derivative, right? So no derivative would mean we have sine theta times the derivative of omega, which we know is just, right, derivative of angular speed is just angular acceleration. So that's what we would get from that, right? And so this right here is really what we would get for our x component. And I don't think we're going to have enough room for our y component, but we're going to see, right? So for our y component, basically our constant is r, and then we're applying the product rule for these two, right? So the derivative of cosine theta, we know is just negative sine theta, and then we of course multiply by the derivative of theta with respect to time, which is just omega, right? Right, times omega, so we get omega squared. And then we add that to no derivative, derivative, right? So we get cosine theta times the derivative of omega with respect to time, which is just the angular acceleration. So we get alpha. So really, this is then we have a j. We fit it all, right? That's pretty much what we get from this. This is the acceleration of an object moving in a circle. Yeah, that's pretty much what this would be. It would be the acceleration of an object moving in a circle, right? Because the radius is constant, this would be our acceleration. But it's not the centripetal acceleration. This is the acceleration of the ball, assuming it's moving in a circle, and it has the potential to move faster in a circle, right? In other words, it could accelerate in the angular direction, right? It has the potential to have angular acceleration and speed up. But centripetal acceleration is not concerned with a change in this speed. It's not concerned with a change in speed of the object. It's only concerned with a change in direction. So really, when it comes to centripetal acceleration, we're ignoring the angular acceleration, right? So we're ignoring angular acceleration, right? We're ignoring that, right? So we're just going to ignore it for when it comes to centripetal acceleration. And so really, what we get is centripetal acceleration if we ignore the angular acceleration, right? That's the whole idea. Now, for our x component, pretty much what this is going to be now is negative omega squared r cosine theta I. And then for our y component, we have negative omega squared r sine theta. So this right here is the angular acceleration. But remember, we're trying to find the magnitude of the angular acceleration because that's usually how you find it. Okay, so to find the magnitude of angular acceleration, we know it's just going to be the square root of our x component squared plus our y component squared. So that's basically all it is, right? So AC is just the square root of our x component squared, so negative omega squared r cosine theta squared plus our y component squared, or negative omega squared r, sine theta squared. Okay, so now we got to simplify this. So how can we do that? Here's how we're going to do it, all right? We're going to actually keep our lives simple. Really, when we're squaring something negative, it's the same thing as squaring the positive version of it, right? So let's just call that positive, right? So what we're going to do is, here's what we're going to do. Really, this is the same thing as omega squared r squared times the cosine squared theta, right? Just roll with this, okay? Plus the omega squared r squared sine squared theta. So in this case, we could factor out omega squared r, right? So AC is equal to the square root of omega squared r, taking that in parentheses and squaring it. And then when we factor that out, we get cosine squared theta plus sine squared theta. Right? And because we get cosine squared theta plus sine squared theta, we know that this is just equal to 1, right? Because this is just cosine squared theta plus sine squared theta, we get 1, right? We know the identity, right? And so really, when we take the square root of omega squared r squared, the square root and the square cancel out. And we're left with the centripetal acceleration equals omega squared r. And so there it is. That's centripetal acceleration. It's pretty much the angular speed squared times the radius. This isn't the only way to express it. In fact, because we know the relationship between angular speed and the speed, right? Remember, omega is just v over r, right? Angular speed is just the speed divided by the radius. So that means omega squared is just v squared over r squared. So if we were to apply this idea to what we have here, right, this might look a little messy, but maybe not actually. Here's how we're gonna do it. Right, this means AC is the same thing as omega squared is just v squared over r squared, so we get v squared over r squared times r, right? And so this is probably the way that you're more familiar to seeing it, right? This is the idea. This is the way they're probably more familiar with seeing it. And so in this case, AC could equal v squared over r. And so this right here is also centripetal acceleration. So as you can see, we have some vector work that we did. It basically is the idea of a circle, and we're ignoring the angular acceleration because angular acceleration implies that we're thinking about a change in speed along the circle, right? But we're not thinking about that when it comes to centripetal acceleration, right? Centripetal acceleration has no component of angular acceleration. And so we're ignoring that. And so as a result, we find the magnitude of our new acceleration vector, and we get the centripetal acceleration. It's the acceleration that causes the object to move in a circle. And that's the whole idea of it. This right here, it's pretty much the centripetal acceleration. That's pretty much it.